All right, today we're cracking open a cosmic cold case, and our subject, well, it's not a person. We're looking at one of the most baffling objects right in our stellar backyard, a pulsar called PSR B0950+08.
And when I say cold, I mean cold. We're talking 17.3 million years old. Just think about that. For 17 million years, this stellar remnant has just been spinning out there, beaming signals across the empty void.
Now, this pulsar has a pretty wild history. It's one of the very first we ever discovered, and its pulses were so perfectly regular, so strange, that for a minute there, astronomers actually nicknamed it LGM-3. Yep, that stands for Little Green Men. It's so important, in fact, that its location is literally etched onto the Pioneer plaque. You know, the map we sent out for any extraterrestrials who might stumble upon our probes. And for over 50 years, from its spot just 260 light-years away in the constellation Leo Minor, it's been sending us signals we still can't fully figure out.
Okay, so here's how we're going to tackle this explainer. We'll follow the evidence, just like detectives. First, we'll look at the cold case itself. Then we'll try to decode those bizarre radio signals. After that, we'll uncover a totally unexpected connection, investigate a faint, ghostly light, and finally, we'll hit a paradox that pretty much turns our understanding of these old stars on its head.
First up, the cosmic cold case. Let's set the scene and figure out what this neutron star has been up to all this time.
So, what exactly is a pulsar? Imagine a massive star that goes supernova. What's left behind is its super dense core, a neutron star. And it's spinning, like ridiculously fast. As it spins, it shoots out beams of radiation, kind of like a cosmic lighthouse. And if we on Earth happen to be in the path of that sweeping beam, blip, we see a pulse.
Okay, so let's get into the first line of investigation, decoding those radio signals.
The first clue we have is the signal itself. And you know, it's not just a simple beep, beep, beep. Not at all. The average pulse from this thing is actually really complex. You've got the big main pulse, sure, but there's also a smaller inner pulse, and even this tiny little precursor signal that shows up right before the main event. This structure is the first piece of our puzzle. But here's what's been bugging astronomers for decades. Why are the pulses so incredibly variable? I mean, sometimes they're super faint, and other times they're unbelievably bright, way brighter than normal.
So this led to two competing ideas. First, you have the giant pulses theory. This basically says the pulsar itself is doing something weird, that it's just blasting out these super powerful bursts on its own. The other idea is interstellar scintillation. This says the issue isn't the pulsar, but all the stuff in between us and it. Think of it like how Earth's atmosphere makes stars twinkle. Same idea, but with space plasma.
Well, after crunching a ton of data, it seems the most likely culprit is that interstellar scintillation, the twinkling of deep space. Case closed, right? Well, not exactly. Because as it so often goes in science, solving this mystery just opened the door to an even bigger one. And this is where things get really interesting. We found an unexpected link, a clue connecting our old local pulsar to one of the biggest mysteries in the cosmos today. So while sifting through all this radio data, the team noticed something strange. These weird, downward drifting patterns in the signal. They looked so unique that they got a nickname, sad trombones. Yep, you heard that right.
And here's why that's a huge deal. The research paper points out that these sad trombones look just like signals seen in fast radio bursts, or FRBs. Now, if you're not familiar, FRBs are one of the biggest mysteries in astronomy right now. They're these mind-bogglingly powerful bursts of energy from deep space that last for just a millisecond.
So all of a sudden, our 17-million-year-old pulsar right in our own galaxy becomes a key witness. It's making a signal that, until now, we'd only seen in these incredibly powerful, mysterious bursts from way out in distant galaxies. Suddenly, this cold case just got red hot.
But the radio signals? That's only part of the story. We need to look at another line of evidence. It's time to talk about capturing a ghostly light.
You know, for years, astronomers struggled to even see this pulsar with a regular optical telescope. It's incredibly faint. But when they finally got an image, a whole new question popped up. What's making this light? Is it just thermal emission, basically the star glowing because it's still hot? Or is it non-thermal emission, something more exotic, created by the same powerful engine and magnetic field that's generating the radio beams?
The verdict came back, and he was pretty clear.
When they analyzed the color of the light, it didn't look like something that was just hot. It had this unique signature, what's called a power law spectrum. That's a dead giveaway for high-energy particles whipping around in a crazy strong magnetic field. So the light isn't coming from heat, it's coming from the pulsar's engine itself.
Okay, and this is where it all comes together. We take our two pieces of evidence, the radio signals and the optical light, and when we put them side by side, we get a massive contradiction. Welcome to the paradox of an old star.
To get this, we just need one more concept: spin-down power. It's simple, really. As a pulsar spins and shoots out all this energy, it spins down. It loses rotational energy over time. And that lost energy, that's its fuel. It's what powers everything we see. So, you'd expect this to be pretty straightforward, right? Young pulsars, they're spinning super fast, they have tons of power. As they get older, they slow down, their power output drops. Makes perfect sense.
So it stands to reason, then, that as a pulsar's power supply dwindles, its efficiency at turning that power into light should also go down. I mean, an old, worn-out engine should be less efficient, right?
Well, that's not what happens. The observations show something completely bizarre. Yeah, young pulsars are efficient, and middle-aged ones become really inefficient, just like we thought. But then, the old-timers, pulsars like our guy, PSR B0950+08, they completely break the trend. Their efficiency shoots right back up. They get way more efficient in their old age.
And that's the paradox. It's a huge discovery that basically throws a wrench in our models of how these things are supposed to work. For some reason, old pulsars are way better at turning their last little bit of energy into light than their middle-aged cousins. It's not a simple case of a star just fading out. Something weird happens late in a pulsar's life that changes the entire game.
It's just an amazing reminder that even these objects we've been staring at for over 50 years can still hold massive surprises. It really makes you wonder, doesn't it? What other cosmic cold cases are just sitting out there, waiting for us to find them and completely rewrite the rules of the universe as we know it?